Welcome to Kines 610, Evidence-Based Practice. Today's online lecture will cover effect sizes and confidence intervals. And to me, these research statistics are important because they kind of allow the researcher to estimate how large the differences are between the groups or the treatments. And this is kind of in contrast to reporting the traditional p-value, which tells the researcher or the reader really if there were differences following the research study. And so the two statistics really truly are different. The p-value tells you yes, there was a difference between the groups, or no, there wasn't, based on whether or not that p-value was below p is less than 0.05. And then the effect size tells you really truly the treatment effect. So how effective was that treatment or the intervention that you perform within that research study? So the purpose of today's online lecture will go beyond the p-value, hopefully, and into more robust research statistics that can hopefully provide you with more clinically meaningful interpretation of your results or the results that you might be reading as you are going through this process of preparing for your capstone project or your master's thesis project as well. So our first stop is with the research hypothesis, right? And so I honestly, you really can't develop a hypothesis unless you have a clinical question. And so the first module of this course, which you all have gone through successfully, is developing the clinical question or the PICO question, right? And this research question will likely help you develop hypotheses that you want to test along the way. So we think about the definition of a hypothesis. It's this proposed explanation of a phenomenon, right? And in its simplest format, there are two types of hypotheses that a researcher usually tests. The first one is the null hypothesis, right? And then the other is the research hypothesis. And so if we define null hypothesis, what we're essentially saying is that there is no difference between the groups or the treatment interventions that are being investigated in your research study, right? On the opposite end of that spectrum is the research hypothesis. It's really what we set out to do. It's a statement that's going to be made by you or another investigator indicating your expectations about the differences between either the groups, the variables, the outcomes, etc., right? One of the things that I think is very important about a research hypothesis is that it's directional, right? And so by directional, what I mean is you expect to see either an increase or a decrease in pain, or an increase or a decrease in flexibility and range of motion following, let's say, a stretching protocol. So as we begin our setting up our research projects, right, whether that be a capstone or a master's thesis, there are two things that we always want to avoid, and one of those things is committing either a type 1 or a type 2 error, right? And so we think about a type 1 error, what we are really saying is that this is an incorrect rejection of a true null hypothesis. Or another way to state it is that we detect an effect or we report there was an effect when in fact there wasn't, right? And so we could say that we report there are differences between the groups, but in fact, guess what? There were no differences at all. On the opposite end of a type 1 error is a type 2 error. And a type 2 error is when you fail to reject a false null hypothesis, or another way to say it would be failing to detect an effect that is present. So this would be horrible, right? That in fact you treat your patient with stretching, there's improvements in range of motion, but you report in fact that there wasn't. You really don't want to commit a type 1 or a type 2 error, right? You really want your research project to be errorless, for lack of better words, and I'm going to tell you different ways to go about doing that through this process of reporting effect sizes and confidence intervals. So in addition to determining if any observed differences from a research study are significant, which would be basically saying reporting whether or not p-value was less than or greater than 0.05, it is also important to estimate how large the differences are between the treatment groups or the intervention groups. And here's where the effect size statistic is so powerful, right? Effect sizes are basically estimates the strength of the treatment, right? It's going to tell us whether or not that treatment was really, really effective, or whether or not that treatment should ever be used in clinical practice ever again by a clinician, or used with a client that we might be working with outside of our clinic. And so it provides an indication of the clinical meaningfulness of the treatment or the intervention that you are actually looking at for your research study. One of the other benefits to the effect size statistic is that it's unitless, which is beautiful, because what it does is it allows us to compare interventions across different studies. Because there's no unit of measure, because we take the unit of measurement out when we calculate the statistic, it really allows us to compare and contrast results from different researchers, different studies that have been published. And what that allows us to do is to truly put together results that would really help drive home whether or not this is an effective intervention or an effective tool or an effective exercise to use to improve patient outcomes in our clinical practice. And then last but not least, and we'll talk about this when we get to calculations, the effect size measurement, as you probably have learned, traditionally, the denominator is going to be the control group's standard deviation. However, what they're finding over time is that the pooled standard deviation between the treatment group and the control group is the more stable of the measurements. And so we'll talk about that as we get into the calculation of the effect size statistic. So effect sizes are traditionally used in one of two circumstances. Number one, when you want to compare groups, right? And so most of the time that's going to be an experimental group versus a control group. However, you can also have a sham group in there, someone who receives some placebo form of treatment, right? And so if it is the case that you are using it to compare groups, then what you're going to do with the effect size statistic is you are going to take the treatment group's mean, subtract it from the control group's mean, and then you can divide it by, which is what I said, either the control group standard deviation or a more stable, conservative approach would be to take the pooled standard deviation between the control group and the treatment group. One other scenario that you could use effect sizes is in your repeated measures design. Some of you are going to do that, where you have one group doing pre and post measurements, and so you would then take the post mean and subtract it from the pre-mean, and then divide it by the mean standard deviation, because this is going to be a smaller standard deviation and probably a lot more stable and not as variable as the post-mean standard deviation. So two ways to calculate effect sizes. If you're using a group approach, then you just take the treatment mean, subtract it by the control mean. If you're using a repeated measures design where you're doing a pre-post design, then you can do post-mean minus the pre-mean. So just like every statistic, it's going to be important to interpret the value of the effect size that you've calculated. And although there are no universally accepted definitions for the interpretation of effect size, the researcher that has been well accepted in reporting the effect sizes is Cohen, and we call the interpretation of effect sizes using Cohen's charts Cohen's D. So if we are using Cohen's interpretations of effect sizes, and then the first thing that we want to pay attention to is this column right here, which is Cohen's D's column. And what that tells you is the size or the effect size statistic. And so what we can see are also the benchmarks and the type of effect. And so what we're looking at really honestly is if we have a small treatment effect, that usually anything below or at 0.2 effect size wise would be a small but beneficial treatment effect. Any effect size at least at 0.5 or above would be considered a medium or beneficial treatment effect. And then last but not least would be any effect size that's reported that is at least at 0.8, if not above, would be considered a large and a major beneficial effect. And so what we can say about effect sizes is this, is that the larger the number is, the more we are convinced that this treatment is way effective, regardless of the p-value. So that's something to keep in mind. Another thing to also keep in mind if you are leaving the social and behavioral sciences is that these values in particular were developed for researchers in the social and behavioral sciences arena. So if you step outside of the social and behavioral sciences, you will have to look for other interpretation charts. So how do we interpret effect sizes, right? So I gave you the scale on the last page, and I said, you know, a 0.8 would be considered large, a 0.5 would be considered a medium effect, and then a 0.2 or below would be considered a small or a null effect. So how do we interpret this? Number one, if statistical significance is found and the effect is strong, so greater or equal to 0.8, the results are likely to be clinically meaningful, right? That is intuitive. It makes sense. The p-value is less than 0.05. Our effect size is at least 0.8. We can take the results of that study and we can apply that to our clinical practice to hopefully improve patient outcomes. But what happens if it's not so clear, right? So if statistical significance is found, but the effect size is weak, so it's less than or equal to 0.2, the clinical meaningfulness of the results must be questioned. So you may not want to use that intervention or that treatment in your clinical practice until you've done further research or you've read other research articles that could substantiate the use or support the use of that treatment or intervention in your clinical practice. As we move on into interpreting effect sizes, I think these are some of the more powerful interpretations. So for example, if statistical significance is not found, but the effect size is strong. So what I'm saying here is that what happens if p is not less than 0.05, it's greater than 0.05, but you have, let's say, a 1.0 on the effect size. That's still very clinically meaningful, meaning this treatment intervention could be a good treatment intervention to use in your clinical practice. One of the concerns that you might have is that when you have, let's say, an effect size that's large but a p-value that was not significant, is the likelihood that you are committing that type 2 error, right? And remember what we said about the type 2 error is that you fail to detect an effect that is present. And part of the reason that you would fail to detect an effect that is present is if the treatment groups are too small. So by increasing your treatment group size, you might actually see statistical significance as it relates to the p-value, okay? What if statistical significance is not found and the effect size is weak? Well, that is straightforward as well. That probably means that that intervention or that treatment probably would not be a good intervention or a treatment tool to use in your clinical practice, okay? Effect sizes should be reported regardless of p-value. So if you have p-value or you don't, a lot of journals really don't care. What they really truly are starting to care about is whether or not those effect sizes are being reported. And so I give you an example or a sample here of a research article that was recently published, right? And so we've got the treatment group, we have the control group, we have the treatment group's mean and standard deviation, and likewise the control group's mean and the control group's standard deviation. And then in this column we have the associated p-value, but what we can also see is that we have the effect sizes associated with the treatment intervention, right? And so we could say that for sure the largest treatment effect in this particular research study was about vertical foot floor clearance following a treatment intervention, and 2.1 is by far a large treatment effect. So I want to read this study and figure out, okay, in patients with ankle sprain, what did they do to improve this particular measurement? And that's something that I would incorporate in my clinical practice to improve, let's say, vertical foot floor clearance in patients with ankle sprain. So as you begin to prepare your master's thesis or your capstone project and you begin to look at journals that you may want to publish in, please keep in mind that a lot of the medical journals nowadays are asking you to report at least the effect size at minimum. And then the one thing that they want you to do in addition to that is also to report the formula that you use, because remember, you can use both the control group standard deviation or the pooled standard deviation, and that becomes important for the reader to know if they want to replicate the study. Now, the effect size is a powerful evidence-based statistic. However, alone, it tells you the strength of the treatment effect, but we also need with it confidence intervals or confidence limits, and we're going to talk about those separately. So I kind of wanted to go through an example of how to calculate effect size. I think in Kinesiology 605 research methods, you guys have learned about this statistic, and I truly do not believe that you are going to hand calculate much because of all of the technology and things that are available online. So I'm going to show you two different tools that can be used to calculate effect sizes, and I'm going to use this study right here because I think it's a powerful study. So it's a randomized control trial of passive accessory joint mobilizations. So for those of you who aren't familiar, you're basically applying manual therapy to the ankle joint in patients who have sprained their ankle, with the goal of improving range of motion. This study was published in 2001. So this particular author sought out to look at two different groups. The first group was a treatment group, and in that treatment group they received rest, ice, compression, and elevation. And in addition to that, the treatment group received a bout of joint mobilizations. So the treatment group had 19 subjects, and then he had a control group, and that control group just received the rest, ice, compression, and elevation, and there were also 19 subjects in that group as well. So what we see is subject balance in both groups for a total of 38 ankle sprain patients, right? So the treatment group had 3 treatments, and then the control group obviously had none as it related to joint mobilizations. And what they found after 3 treatments of joint mobilization is that the treatment group had 23.5 degrees of dorsiflexion range of motion, and then the control group had 16.5 degrees, right? And so that's powerful. There's at least a 7-degree difference in dorsiflexion range of motion, but how powerful is it really, right? And so the way to tell just how powerful that treatment was is to look at the effect size. And so the calculated effect size for the treatment in this particular study was 3. So remember I said that a 0.8 is a large effect, but when we look at the effect size, it's a 3.7, which means that there is no doubt that joint mobilizations, when applied to acute ankle sprains, is an effective tool to use when, guess what, a patient is lacking range of motion, specifically dorsiflexion range of motion. So how did they calculate that? Well, remember there's 2 different ways to calculate effect sizes. The first one is when you have 2 groups. You take the treatment group, you subtract it by the control group, and then you can divide it by the control group's standard deviation, or you can take the pooled standard deviation. So what we're going to do is we're going to exit out of this lecture for just a second, and I'm going to take you into Excel to show you just how to calculate the effect size. Okay, we're back, so this is the Excel effect size calculator. This Excel calculator is actually in your Canvas course, so you can feel free to use this for your homework assignment and also for your capstone or your master's thesis project as well. So what you're going to see within the spreadsheet is the treatment group and the control group. And so when we were looking at the ankle sprain study, we said that the treatment group had an average of, I believe it was about 23.1 degrees of dorsiflexion, and they had a standard deviation of 2.1. And there were 19 subjects in that particular group. And then we said that the control group had an average of 16.4 degrees of dorsiflexion range of motion. Their standard deviation was 1.9, and again we had 19 subjects in that group. So once you put in the data, all of the formulas are already embedded, and so it calculates several different things for you. The first thing that we're going to look at is the effect size. So here's one effect size, and here is the other effect size. So what we're looking at here is the effect size when when we use the pooled standard deviation. And then we're looking at the effect size when we use the control group's standard deviation. So you can see that when you use the pooled standard deviation, you're more conservative, and I'd almost rather underestimate the effect than overestimate the effect and I guess create a type 2 error, right? And so what can we say? That this is a large treatment effect. Also within this spreadsheet, we're going to talk about confidence intervals in the lecture, but the confidence intervals are also calculated for you. So we'll come back to the spreadsheet in just a second, but it's pretty simple to use, right? Another cool online tool to use if you're not, let's say, Excel savvy is an online effect size calculator. The big deal with online effect size calculators is you need to know which standard deviation they're using, and so you can kind of tell within the formula here that they're using the pooled standard deviation. So when you're writing your formula, as you're preparing your manuscript, make sure that you note which effect size calculation is being used. But again, mean 1 for the treatment group would have been 23.1, mean 2, or the mean for the control group would have been 16.4, and then the standard deviation for my treatment group would have been 2.1, and then my standard deviation for my control group would have been 1.9. You hit compute and you get Cohen's d effect size of 3.3. So relatively consistent with the Excel spreadsheet. I don't care which effect size statistic you use as long as it yields the right information. So I've mentioned the word confidence intervals several times, and so the confidence interval is basically the desired level of confidence set by the researcher, right? The confidence level is the complement of the respective level of significances, and so what that means is that if a confidence interval is set to 95%, that confidence interval would reflect a p-value or a significance value of 0.05. And what that basically means is what? That we're 95% confident that the true value of the parameter in which we are assessing is in that interval, or it's not, right? You can also set the confidence interval at 99%. And so what we would say is that we're 99% confident that that true value of the parameter lies somewhere within the confidence interval, right? And so as you increase your level of confidence, right, the more stringent that that variable becomes. So it's important that you report confidence intervals, but more important, it's important that you report whether or not that confidence interval crosses 0. And so here's why. When a confidence interval crosses 0, what that tells us is that the results basically are not statistically significant, right? They may be clinically meaningful or significant, but it tells us that these results are not statistically significant. So we can look at these two different outcome measures, right? And this outcome measure, the confidence interval is relatively wide, right? The point estimate's in the middle, but it never crosses 0. And so what we can say is that if it's set at 95%, that we're 95% certain that the treatment effect lies somewhere within this this interval. However, when we look at the outcome measure on the top, we're not certain, because why? The interval crosses 0, and so we're not 95% certain that the parameter lies somewhere within our confidence interval. So as I said, effect sizes need to be reported along with p-values, but quite honestly, your confidence intervals probably should be reported as well. So how do we interpret confidence intervals? Values near the center of the confidence interval are more plausible than values near the ends, right? So if we were to go back to this slide, what we would say is that values near the center or closer to the point estimate are definitely more precise or more reliable than values that fall way towards the ends of the confidence intervals. And so wider confidence intervals indicate less precision. And so usually if they're too wide, what that means is that there's a small sample size, and then that kind of results in low power. So less precision is closely related or correlated to power. So how do we increase precision and thus power? I think I said it in the beginning, and if I didn't, I'll say it now. The easiest way to increase the study's power and to increase precision is to increase the number of subjects in your study. That will take care of precision and will also increase your study's power. So what am I saying? The more subjects you have, the more subjects you can gather, the more power your study has as it relates to not only the treatment effect, not only the confidence intervals, but just the validity and reliability of the study in general. So we've looked at the Excel spreadsheet for the effect sizes, which are highlighted in yellow here and here. And as I typed in my values for my treatment group and my control group, what you may have noticed is that the confidence intervals were also being calculated as well. And so if we were to take a look at the second row, what you will see is the confidence intervals being calculated. And so here and here, right? And so what can we say? Does the confidence interval cross zero? The answer would be no, right? And so because it doesn't cross zero, we're 95% certain that the parameter that we're assessing falls within that band. Some other key things about the spreadsheet, you can change the confidence interval percent. So if you don't want to be 95% certain and you want to be 99% certain, you can change that. But as you change or increase the percent of the confidence interval, notice that it becomes wider, right? Because as you become more certain, guess what? It becomes more stringent. So just keep that in mind as you change as you're setting your probability values for your research projects. So just wanted to make you aware of that as well. So we've got the confidence interval and we have the effect size. So how do we report that in the literature, right? So it would look something like reporting the effect size here, and then in parentheses we would report the confidence intervals. So it would look something like this here. And that would be the effect size, and then that would be the confidence interval for which it goes through. And I'm sorry, that's actually a 1.85. Right? Okay. So in conclusion, traditional hypothesis testing provides a dichotomous answer to your research question. What are there differences between the group? You can answer yes or no based on whether or not you got a p-value that was less than or greater than 0.05, right? But there are limitations to this approach, right? The limitation is that it doesn't allow you to really truly draw conclusions on the treatment effect, right? The intervention effect. And so that's where the effect size comes in. The effect size provides estimates of the strength of the differences between the group. The stronger the differences, the more we can support the use of that intervention or that treatment in research. And then couple the effect size with the confidence interval, and then we can be even more certain that our strong effect size really truly is purporting what it is purporting to do, right? And so using all three, the p-value, the effect size, and the confidence intervals, reporting all three in combination will provide the best information to not only the reader, but to your clients and to yourself. And it will allow you to not only just interpret the significance of the results, but the clinical meaningfulness of the results. And to me, that is the most powerful aspect of reporting the effect size and the confidence interval. So I'd like to thank you for listening to this lecture. I'm looking forward to facilitating the next module. As always, if you have any questions, feel free to email me.